Bueno, good morning, everyone. I'm working for ASTER, which is a regional agency that is working on bringing the results from the research laboratories and the research centers to the companies in the region. And we were involved since the beginning in the EU's AQ project to try to find what were the opportunities and the barriers in our region to exploit this renewable energy technology. So I'm going to give you a little bit of background about the area where the pilot is so that you can better understand the conditions and the situations, how we proceeded there. As Alicia was explaining to you at the beginning, the challenge now is to make heating and cooling more renewable because it's determining half of the energy consumption in the EU, and in Italy almost the 60%. That's only heating and cooling, so I did not consider hot water production. And as you can see from the graph there, the demand for cooling is increasing, of course, especially in the Mediterranean countries, but also in other countries, also for industrial processes. So this is why we should, we have an opportunity to improve the situation. As for Italy, ground source heat pumps are quite common. This is the number of total plants installed. These are not only geothermal heat pumps, but not only open loop systems. As you have seen at the beginning, there are two types of plants, those that do not imply an exchange of water, and the closed loop systems therefore are more common than the open loop. The region which is more leading in this field is Lombardy, that has worked a lot on the regulatory side, and we are now trying to involve them also to learn from their experience. But a lot is going on also at national level to try to define standards how geothermal heat pump systems should be designed and built so as to guarantee some quality standards for the plants. In fact, there's a national platform that is that puts together the professionals that are involved in this field, so geologists, architects, and engineers, and which is pushing for this technology to be better taken up at national level. Emilia-Romagna is in fact trying to follow and to reach the objectives that are defined at European level. So is also trying to push for renewable energy sources for heating and cooling, and especially ground source heat pumps and district heating are seen now as the main solution to achieve these targets. You see there that in 2014 only 12% of the thermal energy consumption in the region were covered by renewable sources, and the goal is to reach 28% by 2030. And this, in terms of heat pumps, that number includes also air-to-air heat pumps, so not only ground source. But the aim is to double the number of installed heat pumps by 2030. So at regional level, there's the will to increase the use of these technologies. However, so far, so the barriers at local level have been mainly the awareness of the technology. So we are days like today's are very important to spread the awareness of the potential that this technology can bring to increase the energy efficiency and the renewable energy percentage in the building sector. Also, the uncertainties about the financial aspects has been a barrier, so this is what we are also trying to tackle in the project by collecting also the economical data, and as well as the fact that the skills are quite distributed amongst different professionals, so they have to work together and integrate their skills, which is not always an easy task. And last, but certainly not the least, is the point of the regulatory processes, which are rather time-consuming and also quite unclear because of the reorganization of the public administration. So these are often a reason for clients not to prefer this option, and that's why also with this project, we want to try to push the regulatory agencies to find a bit easier pathways for this technology to develop. And from their perspective, what they have been sharing with us, the main concerns are the risks of putting in contact different aquifer systems, or to avoid that thermal anomalies can be generated along the areas, and of course that any chemical pollution may arise from the plants. So these have been the points of attention from the regulatory point of view that also were required to be addressed during the pilot. And I think this was a little bit of the context, and now I leave the word to Marco Pellegrini from the University of Bologna, that's going to explain you more in detail what the pilot case in Italy is about.
Thank you, Sara. Okay, so I will speak to you about the Italian pilot, just a few information about the activities that have been carried out in the last 3 years. We still not have a pilot, so we are working on it. We started the realization of the civil works last month, and I guess we will finish all the installation hopefully by the end of the year. We lost a lot of time, as Sara said, in the authorization process and also in the identification of the company that has to realize the plant. It takes a lot of time, this kind of activity. By the way, this is the site. We are in an electric station. So here you can see the electric station. And in the electric station, there are 2 buildings that host, that host offices. It's the building B. And the building A is like a recreative section for the workers, where you have a kitchen, you have also restroom, showers, and so on. What is interesting to say is that these are 2 buildings that have been realized in the 1780s, so are a good example of Italian installation, I would say, also from an architectural point of view. And so they are not really performing from an energetic efficiency point of view. This is a 1-floor building, this is a 2-floor buildings, and this one has more or less 1,500 cubic meters of conditioned volume. This one has more or less 5,000 cubic meters. And the situation when we arrived at this site was this one. This is the building A, and this is the 2 floors of the building B. This is the conditioned area, and this one are some rooms that need always cooling all over the years, because there are computers, electric panels, servers, and so on. So they need cooling also in winter. There was a complex systems of plant that origins from a sort of stratification. So year by year they just add some further plants to produce heat or cool, that it is also a quite common situation. So we have methane boilers or water-to-air heat pumps for space heating, electric boilers for domestic hot water production, and also water-to-air fan coils and chillers for space cooling. And the two buildings are separated in terms of energy production, cooling and heating, so they are independent. So when we approach the problem of doing a pilot in this site, first of all, we have to convince the plant owner, that is Terna, that is a private company that is controlled by the ministry, by the Italian minister, and so it's quite like a public company indeed. And they agree to make this kind of realization, but they have no idea of the aquifer characteristics that was under the electric station. They know that there is an aquifer, but they don't know how much more than that. And they also didn't know how much about the energy cost, because they are in an electric station, and so for their electricity is not a cost. So that's why they were really happy to move to electricity and avoid the use of methane in methane boilers. This was a cost that they know very well. And they also have no idea about the authorization process, so how to approach with the regional authority and how to finalize the authorization process. These are some information of the final results of the design. Later on I will show you how we can get to these final results. We have several wells. The yellow one are monitoring wells, so they are used only to measure the temperature of the aquifer and the level of the aquifer. While these three are extraction wells, so from these wells we pump the water from the groundwater, we send it to a technical station where there is a heat exchange between a primary circuit and a secondary circuit. They take the heat or the cool to the buildings, and then we reinject the groundwater here in these red injection wells. So we have 6 production wells, 3 for extraction and 3 for injection, 4 monitoring wells. The well's depth is 30 meters. We have a maximum groundwater flow rate of about 20 cubic meter per hour. It's a total amount, so it has to be divided by the 3 extraction wells. And the power of this plant is, the maximum cooling power is 140, while the heating power is 160. So it's just few data about the pilot plant installation. This is a P&ID, piping and instrumentation diagram. Here you can see the 3 extraction wells. The heat exchanger, we decided to double it so we can avoid the stop of the plant if we hope that there is not this problem, but if there is problem of clogging of this heat exchanger, we can use this one. So there is the opportunity to guarantee the continuity of the plant, also if we will have this kind of problem. And here we have the injection wells. And here is a look to the heat pumps and chillers side. So the water that is the heat or the cool that is taken from the heat exchanger. So we have this one that is the primary circuit, and we have a secondary circuit that takes the water to the heat pumps and the chillers. And here we are. This is the plant for the building A. And this is the plant for the building B. Here you can see the heat pump and a thermal puffer where you can store heat or cool depending on the season, and that is integrated by other backup units like electric boilers and so on, or the existing air-to-water chiller. And this one is more or less the same. Here we have two heat pumps. These heat pumps are reversible heat pumps, meaning that they can work in summertime as a chiller. So simply by make a reversible operation of manual valves, you can use them to produce cold or heat, depending on the season. Why this one is only a chiller? As mentioned before, there are some rooms that always need cool all the year long, also in wintertime. So this machine produces cool also in wintertime. And this is an interesting application because, as you can see, we realized a sort of really small, because we have two buildings, so it's the minimum number to call it district heating and cooling. So it's like an experimental installation in real scale. And at the end, we will have all the kind of instrumentation and control strategies that may be applied to a larger number of buildings. But this kind of installation will be interesting because we will have to manage two separated buildings, so with different requests from an energy perspective. And it is also interesting to evaluate this combination because when the heat pump works as a heat pump in winter, the heat pump takes heat from the secondary circuit, and contemporary, this chiller will give it to the secondary circuit. So there may be a balance, an energy balance in this circuit. So probably we will see that in some condition, this building will not use geothermal energy, but the system, in particular the secondary circuit, will be used as a sort of heat exchanger to bring this reacted heat by the heat pumps to the rooms that need the heat. It is a quite interesting application to be used also at district scale. So the question is how the pilot plant has been designed. So this is the final result. But how we came to this, it's a long story. So I will try to be quick as possible. First of all, as I mentioned it before, we had really poor information about the energy consumption. We have some information about methane consumption, but no idea of the electric efficiency of the machine that were installed in the electric station. So what we made was an energy audit. So we characterize the buildings from architectural point of view, try to see which are the dispersion and so on. And we make some simulations, and at the end we have this kind of results. So we have a total, for example, peak request regarding heating that is about 150 kilowatt, while the cooling, and it is quite interesting, is higher. So we have a peak demand of cooling that is higher if compared to heating, but the energy is completely different over the year. In the two buildings, you will need more or less 170 megawatt hour per year, while in cooling you are more or less at 50. So there is a sort of imbalance between the heating demand and the cooling demand. After that, we have to characterize the aquifer characteristics. As I mentioned before, there was no idea of which kind of aquifer was above Terna site. And I have to say that they initially thought that there was a big aquifer at a depth of about 80 meters. And that's why they were so keen to realize this kind of plan. But we made an investigation, so we make a borehole up to 100 meters depth, and we find only a small aquifer, more or less between 22 and 30 meters, so a real thin layer of, we guess, 3 meters of water. And obviously at 80 meters that was no aquifer. So we have to consider only this one as a potential source for our plant. And that was really important. We made a preliminary pumping test, meaning that we realize this well, then we put it in a pump, and we try to pump as much as possible. And here you can see the result of this preliminary pumping test. Here there is the flow rate, and here you have the water level variation. So until you are linear, things are going well, but starting from this point, you are pumping too much water. So the risk is to drain the aquifer. So we have to stop here as a water flow rate from one well. And that was a really important information to size, to design the extraction system. So we have 3 wells to reach the groundwater flow rate that is needed to feed the heat pumps and the chillers. If we need more water, we have to realize more extraction wells and more injection wells. That means higher cost, as you will see. Another thing that this one was requested by the regional authority. It was a study of the thermal plume. The thermal plume is a sort of temperature variation that is produced by the plant when the plant is in operation. Obviously, you take the groundwater, you exchange it. So in the winter, you will cool down the aquifer, and in the summer, you will heat it up. So you have to consider year by year the effect of this heat exchange, and you have to be sure that these do not produce unexpected problems. So the region asked us to realize this kind of study that was made by a geologist, starting from the information of this pumping test and taking into consideration data coming from literature. And you can see here, these are the 2 buildings, the building A, the building B, and the system might create a sort of thermal plume that is moving in the same direction of the groundwater flow. We also made further pumping tests to simulate the real operation of the plant. So we complete the realization of the wells, as I show you before, and we made a pumping test where water is extracted by the 3 extraction wells and reinjected in the 3 injection wells and monitored the situation. Here you can see the depression in terms of level that is created by the water extraction. And here in the injection area, you can see the water level increase that is generated by the injection. And what is interesting to see is that we can identify by this shape a sort of direction of the flow rate that is quite similar to the one that we imagine based on literature data. Another important thing is that we were able to measure the groundwater ambient flow velocity that result as really high, probably due to the thin layer of aquifer, and for the condition of this specific site, we have a really high velocity, and so that's why we decided to use this kind of approach, which is quite different from the one that is used in the Netherlands, where you have a sort of static aquifers. So you can use a cold well and a heat well and a warm well instead of call it extraction and reinjection, because depending on the season, you can reverse their functioning. While in this kind of conditions, it's better to use this kind of strategy. So you always extract water from these wells and inject the water in this one. We also made a tracer test to see if there is a risk of what is called thermal short circuit. So if we extract here and pump the water here, there is the possibility that the water that has been pumped here is taken by the pumps. So we create a sort of circuit that is not good, because if we cool down the water and pump it, then we will use cooled water. And so the efficiency of the system will go down in wintertime, and obviously the opposite can occur in summertime. So we make this test. We pumped in injection water a mixture of groundwater and salts, and after pumping for about I don't remember, maybe 4 or 5 hours, then we stopped injecting this mixture, and then we continue pumping and measure the electrical conductivity variation in the extraction well, and we found that after few hours there was a variation in the electrical conductivity, meaning that there was a short circuit. Another thing that we've done is a chemical physical analysis. So we take a lot of sampling and make this kind of laboratory analysis. A first problem that was found was the presence of benzene, and that was a problem with the regional authority. They were afraid about this kind of presence. And so we repeat the test after 6 months. We didn't find that, and so they said, okay, you can go on. Probably there was a sort of one spot measurement. While a constant characteristic is the higher presence of manganese, that would be a problem for clogging. So we made several tests, and we are quite sure that the characteristics of these manganese should be not a problem for the realization of the plant in terms of clogging potential. And what about the authorization process? Well, Italy, it's a beautiful place, and for this kind of application you need 2 authorizations. One for extracting water and one for injecting water. So obviously, if you extract the water, the guys that give you the authorization say, oh, you have to put the water back in the groundwater. But you need another authorization from another guy that is quite near the desktop of the other one. But it is a funny story. And so what we have to comply to have this kind of authorization? First of all, we have to guarantee that the temperature variation is in the range of 5 degrees in terms of cooling or temperature increasing. So we have to work in this range. No chemical and physical alteration of the groundwater has to be produced, meaning that we cannot work, for example, on manganese by making it precipitating or filtering it. We have to work with this water and we have to put it back as it is. And they also asked, obviously, for further monitoring well. So in the first version of the design, we plan to realize three monitoring wells, and they asked us for one more. And what asked the agency, the regional agency for the groundwater injection, they said you have to make yearly monitoring of aquifer impact. So you have to take sample, make chemical physical analysis, the one that I showed before, and see year by year if there is an impact. And obviously you have to measure the volumes of groundwater that you extract and that you reinject, because they have to be similar, closest as possible. So meaning that you don't use the groundwater to do anything else that feeding the heat pumps and the chillers. What about the cost? The total investment is quite high, as you can see. 460,000 euros, but this cost includes a lot of different things that are not strictly related to the realization of the plant. For example, there was retrofitting of the existing distribution system that was not needed for the ATES realization itself. And an extra cost also have to be considered in this investment due by the specific characteristic of the site. So they want to be sure that all the systems are cooled down and that the offices are comfortable all the season due by the specific characteristic of the site. That is an electric station. So they want to be sure that everything is right in operation. I also put here some information that are interesting because they are costs that you may invest even if at the end you do not realize the plant. This is an option. You may realize your well that costs more or less 50,000 euros, do the pumping test, that is an extra cost, and you realize that you have not enough water to feed your system. We made also a test with a tracer, and so you can have an idea of the costs. And also the authorization process is a cost, because they ask for a thermal plumb study, and you have to prepare obviously a report and so on. And so this is an important part of this kind of activity that has to be taken into account when you want to realize this kind of installation. And these are a few pictures of the realization of the wells. These are the 1 meter column. You can see clay and silt, that are predominantly. And these are the 3 meters, more or less. When you can find the aquifer, you can see the sand and some rocks, small rocks. So here is when we found the water, and here you can see the start of the realization of the civil works that, as I said before, started in September. And so the things are going on, even if a little bit slowly than in Spain. So thanks for your attention.